So just as a little intro, there's quite a bit of stuff that I'd planned to get through yesterday that we didn't get to. And I'm just going to gloss over it really quickly, and then we'll jump straight into the RSA stuff. And if we end up, for some reason, having a lot of time or some extra time, we can come back and spend some more time on this, or really on anything else that you have questions on or that you'd like to work on a little bit more. So we worked through the two ways of programming the Caesar cipher, and then just wanted to point out if we were to try to hack it here. Is that a little better? Can everybody see that? It's big enough. If we were to try to hack it, essentially, there's a fixed number of keys. The keys, in this case, are derived from letters of the alphabet. So we can map from enum over the list of letters in the alphabet from this generated range. And we can then zip that up so that each key then is in a tuple with a list, with a copy of the encrypted text. And from there, from there we can really just fmap over the list of tuples. And for each tuple, we can attempt to just run our same encrypt function in decrypt mode with the key minus the starting character enum number for A over the message, and then just one of those is going to work, right? So we can just brute force it pretty easily. Transposition cipher. Here's the fast way, the cool composition form from yesterday. Also part of this was going to be showing how to hack it. And so in order to hack this one, there's potentially for every transposition cipher, you can have a key for each character that is in the message. So decrypting it can get pretty bonkers if you're brute forcing it. And so we want a way to not just be able to do that with our eyeballs, but be able to have the computer help us out. And so this demonstrates a method of loading in a dictionary file of English words, and then getting a count of the English words, and finally just saying, like, look, it's pretty if we have at least 20% English words, then we've probably hacked it, because it's pretty unlikely that there are 20 random solutions that we found here. So then with hacking this, we can use the 4M monad control structure, which takes a list of things and a function that returns a monadic action, and it runs that action for each list of the things, for each thing in the list. And so if there's ever been a time where you've wanted to do something like say you've got a list of 3 integers, and you'd like to do something like you'd like to fmap over it, and instead of doing something like adding a number, you actually want to do put string line. So we run into some troubles here. So we need to, because the I/O monad gets us in trouble with the type system. And so there's a couple of options here, and one is to use this 4M control structure, which takes a list of things, and then we can And then we can finish with a function that returns a monadic action. So that can come in pretty handy. There's some pretty fun performance stuff here that we can dig in later. But the core of this is remembering that the data.txt package provides fusion over almost every one of its methods that it exports that works on large text pieces. And so when we can compose the functions together like this, we can actually get a very good big O complexity time for our algorithm. And maybe we can demonstrate this a little bit later, but using this, we can both not just encrypt entire books, but brute force entire books really just in milliseconds. And so we'll jump into that. But want to get into the thick of it today and talk about RSA. So imagine we got it all together over drinks last night of Monadic Party, and we came up with a big plan that we were going to introduce functional programming everywhere we worked. But we knew that the IT overlords are very big OO fanatics and that they're monitoring all our communications. So we can't communicate in plain text, right? And so we decided, oh, well, we'll just leverage the encryption that we've learned, and we'll encrypt our messages back and forth so they won't know. And sometime between drink 5 and who knows how many, we forget to exchange encryption keys. So the question is, what could we possibly do? And the answer is that unlike the methods that we've used up to now, we can use an asymmetric encryption method. And so a symmetric encryption method uses the same key to encrypt and to decrypt the message. But an asymmetric encryption system uses 2 keys, one to encrypt and 2 to decrypt, the second to decrypt. So to make this work, what you can do is you can share your public key with your friend, and they can use it to encrypt communication that they're sending to you. And you can keep your private key safe and secret. And then you can use that private key to decrypt the messages that are coming in. And I do want to note here that this system really only guarantees encryption, not authorization. So it doesn't guarantee identity. So if, for example, when I send my first email in plain text with the public key, our IT overlords are sitting in the middle and they intercept the public key, then going forward, the IT person could get the messages that are being sent to them, and instead of encrypting it with the public key that I sent out, they could encrypt that message with their own public key. And once they do that, they could forward it on to you, and you would be none the wiser. And it could work both ways. So a person sitting in the middle could be forwarding a communication over, and to both of us, it would look like everything had been encrypted and everything was working fine. But in the middle, they would be intercepting the traffic and decrypting everything. So the question is, how can something like this work? And really what we need is we need something where even if the encryption mechanism is known, that it's still basically impossible to brute force, which means that we need a type of computation that is extremely easy to perform one way, but extremely difficult to perform the other way. And the strategy that has been established, basically all of them rely around really, really big primes. And so in order to do this, we really need to find a way to generate some really big numbers and then determine efficiently whether they're prime or not. because we're going to need to have a prime number that is extremely, extremely large and also randomly generated. And so this is going to test us a little bit in terms of what we can do with both performance and computation and math. And also, it's going to give us some practice with random number generation with the I/O monad. So one strategy is to use some kind of sieve. The most really famous of which is the sieve, I think, of Eratosthenes. And this is the algorithm for this sieve. So first, you take a list of all possible numbers. And we know that, no even numbers are going to be prime. So we can just eliminate all of those. We can just mark them off. And then the definition of a prime number, of course, is something that only has the factors of 1 and itself. And so that means if we start with the next number and we eliminate it and also all of its multiples, then we've crossed out an entire group of prime numbers. And then of numbers that aren't prime, of composite numbers. And so then if you started off and you went to the next one, to 4, and then you eliminated all those, and you kept going as long as there were numbers in your list that weren't eliminated, you would eventually end up with numbers that were only prime. And typically when you're doing this, you stop at the square root of the number that you're trying to determine is prime. And the reason for this is that when you're looking for multiples, there's always a lower multiple and a higher multiple. And we can stop at the square root because at that point, all of the lower multiples that we have found will be corresponding pairs to higher multiples that are above the square root. However, Haskell is pretty awesome, and the laziness of it allows us to completely ignore that optimization and also several others. And so really, we can use a list comprehension plus some pretty interesting operators to generate an infinite list of prime numbers. So I want you to take just a few seconds to take a look at this right here, and then see if you can work out what's going on, and then we'll break it down because it's a little complicated.
Can you make it slightly bigger?
Uh-huh.
Thank you.
Whoops. Sorry, jumping around like crazy.
Is minus the same as the double backslash?
Sorry, so minus, and I'll bring this over here so that we can. So minus, union, and union all are in the data.list.ordered function. And so minus performs the operation of subtracting elements from one list that are members of the next list. So it's very similar to set subtraction. And so if, let me see if I can, Okay, so minus takes two lists and returns a third list. And so if we do minus and we do a list of, let's do of all numbers and then a list of even numbers, we get a list of odd numbers.
So, is it basically a filter not alarm?
A filter and
Not alarm?
yes, but the issue with elem is that elem must check every element. And so we need a way to operate on infinite lists lazily
Okay.
because we want to do the sieve, but if we evaluate, then we'll never finish. So that's why here, if we actually do minus 1, 2, 2, 4, this is, right?
Yeah.
Now we've got a problem. So yeah, so that's what's going on there. So then let's take a look at union. Takes two lists and gives us another list. Better? So union returns both lists with each number repeated the most times that it is in one list. So if we change this so that we have 3 3s or 3 2s in this list, we get 3 2s in the resulting list. Union all does the same thing, but for a list of lists. So instead of having to map over a list of lists with another list, you can just give it.
So it's concat map union.
Yeah.
Does it sort at the same time, or is that just arbitrary from what you put in?
It doesn't sort at the same time. So it only guarantees that, so even here you can see, now it breaks up the 2s. Okay, so let's break this down. So kind of what makes this really difficult is the fact that this list comprehension is a recursive data structure itself, right? So first let's think about what's going on. So we have 2 cons to 3, and let's for a second ignore the minus. So 2 cons to 3 cons to 5, 7, ... what's that going to be? 2 plus all odd numbers. Sorry? Except 1. And so then we have minus with the list of all odd numbers greater than 5 or greater than 3 with this union all. And so we can intuit that actually what's going to be going on here is we're going to want to minus from the list of odd numbers any numbers that are composites. And so this section here is the sieve, where everything here are going to be the numbers that we eliminate from the odd number list. So then we have union all. So union all is there because we want to make sure that we only have one of each of the numbers that we're eliminating. So we don't want to get 25 in there 4 times and eliminate it. We want to make sure that it's there only once. And then we have here another generated list, p times p, comma, p times p plus 2 times p going forward. And so what this is this is going to be a list of numbers that are multiples of p, where p is the first element in the tail of our infinite list. And so the tail of primes when we start is going to be 3, or is going to start with 3. And so union all is going to take all the multiples of 3. This section is going to make sure that we have only one multiple of 3 and remove all those multiples from the list of odd numbers. And then it's going to do it with the next one, which is 5, and the next one that's 7. But since it's not taking, we could do something like this and accomplish something very similar. But since we're eliminating numbers from the end of our infinite list as we go, we're actually getting a much more performant scenario. Because after this runs the first time, all the multiples of 3 are going to have been eliminated from primes. And so we're not going to hit 6 ever, or 9, or any of the, we wouldn't hit 6 because it's even, but any of the odd multiples of 3. And we're not going to hit 21. And then as we go forward, there's just less and less options of anything that there can be. So this is, I think, just an example of how dang cool this language can be. And quite expressive, if a little bit sneaky. But so let's, okay. I may have to. So there's 100 prime numbers. There's 500 prime numbers. There's 1,000. So we start getting into trouble still, though, when this is pretty big. Starts taking a long time. So even though it's fast, unfortunately, this method alone for our purposes is not going to be quite good enough.
Can you run it without printing it the screen, but still evaluating it? Because maybe it would be.
Yeah, so still pretty much faster if we don't print it, but we're going to need to do something like oh, so actually, and this is one of the problems, though, is that even with take, until we use it.
Yeah, I know. I was thinking maybe some kind of switch or something that you can
To
say
force the
this way,
evaluation?
force it, yeah.
You can just take exclamation mark, find exclamation point an 11, for example.
Say again?
Or just pick out element number 1,000,000 with exclamation marks. So primes. So,
Other way?
decision on argument.
It's more than 1 million, I think.
I don't think we have time.
More. 10 billion, isn't it?
Yeah. But we're going to need numbers that are very big. And so this is not going to do it for us. It's going to really help us out, though, because a very cool trick for determining if a number is prime is to just see if it's a multiple of one of the first 100 to 200 to 500 primes. So almost every number that is really giant is a composite of one of those first 100 primes. And so we generate a list of primes. That is going to come in handy for our algorithm. But we're going to need something else. And so here what we have is an implementation of what is called the Miller-Rabin primality test. And this is about the best that I could do without having an advanced math degree. And still, this is code from the Haskell wiki. And what this relies on is a couple of properties about modulus arithmetic and prime numbers. And it's a fast way of almost assuredly proving that a number is prime, but not 100%. And this is one of the reasons why our implementation of RSA is not going to be secure, is because this method of determining if a number is prime can fail. And if it does, then our encryption is going to be completely faulty. But the situation here is that we can utilize that check plus the check on our that I spoke of earlier. So our quick prime check can say, hey, if n is greater than 2 and it's and that n is not and that none of the first 100 primes are a factor of n, and the Miller-Rabin primality check works, then we should be reasonably sure that what we have is in fact a prime. So beyond that, we just need to do the job of generating very, very large random numbers and then testing to see if they're prime and then moving on from there. So I want to take a chance here to do like a quick dive into monadic do notation in particular, or in general, the IO monad and generating random numbers in particular. So the rules of do notation are they're pretty simple. So the first one is, if you want to do something, if you want to capture a value with a computation that doesn't need or that isn't monadic, just use a let expression. So that's the example here. let min bound equal this arithmetic, let max bound. This could just as well be here. Any other pure function that we have. Right? And so anytime you need to capture a value to use that isn't monadic, just use a let expression. Second rule is, if you want to capture a value with a monadic computation, use the backwards arrow. So that's the example here. So random RIO is returns a type that is a number wrapped in the IO monad. And so in order to capture that number for use later on, we use the backwards arrow. If you want to run a monadic computation and forget about the value, just run the computation. So that example here is put string line. There's really nothing sensible that we can really capture from put string line. And so trying to do something like this, we can't really do anything, but that doesn't mean that we can't run the monadic computation. We just run it as is. And the reason for that is if we go over here, we can see that put string line takes a string and returns an IO of unit, which is essentially the empty value. And because of that, so if we did capture something here, we could do it with value pattern matching because it's always going to be the same thing. It's never going to be anything but unit. And there's really nothing that we can do with it. But capturing it like this and throwing it away, so capturing like this and never using it and throwing it away, exactly the same thing. So finally, always the last statement has to evaluate to the type of the monad you're operating in. So in this case, this function is an IO monad. So the last statement has to evaluate to an IO monad. So here, how could I simplify what I've got right here to follow that rule? Without having So at this case, the random Rio is going to run, and it itself already returns an IO monad. So all return does is it lifts a type into the monad of whatever context you're in. And so the compiler here understands that we're in an IO monad because of the random RIO action. And so this is essentially unwrapping it just to wrap it back up again and return it. So really to demonstrate to the class what to do, but it is really useful to operate on those numbers, because if we wanted to do something like square that number, multiply it by itself. Now we have the result of the arithmetic returned wrapped up in an IO monad. And so then this would make sense. But because you can't operate with multiplication on random RIO, min bound, max bound, because the IO monad is not an instance of num. Is that clicking? So people make a big deal about doing input and output in Haskell and using the IO monad. But really, if you just focus on these 4 things and use do notation, it's not that bad. And if you want to learn more about it or get more comfortable, then you can then just remember that anytime you do this kind of a thing, that is just syntactic sugar over the bind function. And every time you do the IO thing and you throw away whatever the result is, that's just syntactic sugar for this operator, which are both defined on every monad that exists. And so you could write the same thing out with nested function calls and a whole bunch of parentheses. It would be really hard to read exactly the same way, and I would mess up the parentheses at least 4 times. But if you understand these simple rules, it should help a lot. Okay, so generate random. We just get a min bound, which is 2 to the 1023. And we get a max bound, which is 2 to the 1024. And we're choosing 1024 because this is the going to be the key size for our encryption keys. And then we get a random number in between those two, and we pump it back out. And so now what we need to do is we need to keep doing this until we find a prime. And it might seem like this is, again, pretty tricky in Haskell, but it turns out really not. This control.monad.loops package is where you want to go anytime you need to repeatedly evaluate IO, or do anytime you're like, oh, I need to map or I need to fold, but I'm dealing with an IO action. Go to control.monad.loops. It's going to be your best friend. And it translates over pretty much to anything that you would ever want to do inside of a imperative language. So some of these look a little weird, like fork map, but while m, execute an action repeatedly as long as the given Boolean expression returns true. The condition is evaluated before the loop body. Collects the results into a list.
Can't you do this with until as well?
With what?
Until?
Yep, until will work. This one has some like specific like until m ones. There's another one that you may have seen is fix. Have you seen that? Yeah. So I find this package to be, so given that you're already in the context of the IO monad, I think that programming a little bit imperatively is not the worst thing in the world. If you push your like business logic and all your domain computations out, then it's not the end of the world to program a little bit imperatively, and really that's what this package lets you do. And so, for example, let me see. So let's just take a look at this and see if we can use one of these. So until m, execute an action until the condition returns true. The condition is evaluated after the loop body, collects the results into a list. So getLine takes an IO string And so let's do just like a multi block here, and let's do a do. And let's say until m, here, actually, I want to use one that let's use one that doesn't wrap up the Boolean inside of a monad first. Let's use one that's a little bit more intuitive. Okay, so this function, until just, is going to take a m of maybe a and a function that takes the a to m of b and then returns an m of unit. And here in this case, what we can do is we know we're going to be operating in the IO monad, so we can take all the m's and we can think IO. So we're going to have an IO action that is going to be closing over a maybe value of a type A. And then we're going to have a function that takes in an A and returns the IO action of B. And then that is going to return an M of unit. And this discards the results, and we can see that because of the way that this function returns unit at the end. So let's see if we can get this to work. So we're going to start a multi-line comment or a multi-line expression, and we're going to do. And so first off, we're going to use while just with the underscore. And then the next value that we're going to need is an m with a maybe of a. So what if we do, one thing that we can do, see if we can find one out of the box for us. We can do this. We can do while just and we can say so now we need an m of maybe a, so we can say put string line we're coming up right against the break, so now my okay, we're going to do get line. Do. Get line. Return just C. So we've got a do block that is going to grab a C and then return just C. And then we need a predicate function that takes in an A. And we could do something like just anything return true. We need just C to wrap it up. I might have forgotten some indentation. Yeah, so I messed up the brackets. It's break time. Let's take a break